Group 1 elements, alkali metals. Electronic configuration. The alkali metals have one electron in the s subshell of their valence shell, while alkaline earth metals have two electrons in the s orbital of the valence shell. The general electronic configuration of group 1 elements is noble gas Ns1. Electronic configuration of alkali metals. These elements can readily give loosely held electron to give monovalent M-positive ions. Hence, they are never found in free state in nature. Atomic and ionic radii. The alkali metal atoms have the largest sizes in a particular period of the periodic table. The monovalent ions M+ are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on moving down the group. The increase in size is due to the addition of extra shells of electrons as we move down. Ionization enthalpy. Because of the weakly held s electron in the outermost valence shell being far away from the nucleus, the ionization enthalpies of the alkali metals are considerably low and further decrease down the group from lithium to cesium. Moreover, the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. Hydration enthalpy. The hydration enthalpies of alkali metal ions decrease with increase in ionic sizes. Lithium plus greater than sodium plus greater than potassium plus greater than rubidium plus greater than cesium plus. Lithium plus has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. For example, LiCl.2H2O. Physical properties. Flame coloration. The alkali metals and their salts, when introduced into the flame, give characteristic color to the flame. The heat from the flame excites the outermost orbital electron to a higher energy level. When this excited electron comes back to the ground state, it emits radiation in the visible region. This property of the alkali metals offers a very sensitive and reliable test for alkali metals. Density. Alkali metals have large ionic size and their atomic nuclei are widely separated in their crystal lattices. The densities of alkali metals are low as compared to other metals, with lithium, sodium, and potassium being even lighter than water. Density gradually increases in moving down from lithium towards cesium. Melting and boiling points. All alkali metals are soft and have low melting and boiling points. They can be cut with a knife. Both melting and boiling points gradually decrease in moving down from lithium to cesium. Thermal and electrical conductivity. Alkali metals are good conductors of electricity and heat due to loosely bound valence shell electron. Chemical properties. Due to their low ionization energy and large size, Alkali metals are highly reactive. The reactivity of these metals increases down the group. Reactivity towards air. Alkali metals get tarnished in air due to the formation of oxide at their surface, and hence they are stored in kerosene or paraffin oil. Rubidium and cesium are typically stored in sealed glass tubes to eliminate contact with air. They burn vigorously in oxygen, forming oxides. With oxygen, lithium forms lithium oxide, Li2O. Sodium forms sodium peroxide, Na2O2, and other elements form superoxides. M plus O2 give MO2 superoxide. M is equal to K RbCS. Lithium also reacts with the nitrogen in the air to produce lithium nitride and is the only group 1 element that forms a nitride. 6 Li plus N2 give 2 Li3N. Reactivity towards water. The alkali metals react vigorously or even explosively with water to form hydroxide and dihydrogen. 2M plus 2H2O give 2M plus 2OH minus plus H2. M is equal to an alkali metal. Sodium also floats in water, but enough heat is given off to melt the sodium. It melts almost at once to form a small silvery ball that moves rapidly across the surface. Potassium also behaves like sodium, except that the reaction is faster and enough heat is given off to ignite the hydrogen. Cesium explodes on contact with water. Reactivity towards dihydrogen. All alkali metals react with hydrogen to form hydrides that are ionic in nature, M plus H minus. The alkali metals react with dihydrogen at about 673 K, lithium at 1073 K to form hydrides. General formula MH. 2 Li plus H2 give 2 LiH. 2K plus H2 give 2KH. 2Rb plus H2 give 2RbH. 2Na plus H2 give 2NaH. Ionic hydrides are solids. They are thermally stable. They have high melting and boiling point. They also form complex hydrides which find applications in synthesis of organic compounds. Reactivity towards halogens. All the alkali metals readily react vigorously with the halogens to form ionic halides M plus X minus, where M is an alkali metal and X is a halogen. For example, 2M plus X2 give 2MX, X is equal to halogen. 2Na plus Cl2 give 2NaCl. The reactivity of the alkali metals increases as their IE decreases. The reactivity order is cesium greater than rubidium, greater than potassium, greater than sodium, greater than lithium. Due to the high polarization capability of lithium ion, its halides are somewhat covalent. The Li+ ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since an ion with large size can be easily distorted, among halides, lithium iodide is the most covalent in nature. Reducing nature. It takes very little energy to remove the outermost electron from an alkali metal. Thus, alkali metals easily lose their outermost electron to become a +1 ion. Therefore, the alkali metals are very strong reducing agents, lithium being the most and sodium the least powerful. The standard electrode potential, E theta, is a measure of the reducing power of an element. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia to give deep blue solutions which are conducting in nature. This happens because the alkali metal atom readily loses the valence electron in ammonia solution. Both the cation and the electron combine with ammonia to form ammoniated cation and ammoniated electron. M plus X plus Y NH3 give M NH3X whole positive plus E NH3Y whole negative. The blue color of the solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. 2M plus 2NH3 give 2MnH2 metylamine plus H2. Uses. All the metals are shiny. They are so soft that they can be cut with a knife. Most of them are white. Cesium is yellow-white. Uses of lithium. Lithium is used in lubricants, in batteries, in glass industries, and in alloys of lead, aluminium, and magnesium to make them less dense and stronger. For example, it is used with lead to make white metal bearings for motor engines. Uses of sodium. Sodium nitrite is a principal ingredient in gunpowder. The pulp and paper industry uses large amounts of sodium hydroxide, sodium carbonate, and sodium sulfate. Sodium carbonate is used by power companies to absorb sulfur dioxide, a serious pollutant, from smokestack gases. Sodium carbonate is also used in the glass and detergent industries. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Sodium chloride is used in foods and to soften the water. Uses of potassium. Most of the potassium is used in making the fertilizers. Potassium hydroxide is used in detergents. Potassium chlorate is used in explosives. Potassium bromide is used in photography industries. Uses of rubidium and cesium. Rubidium is used almost exclusively for research, but cesium is used in special glasses and radiation detection equipment.